Yeah, it's recording.
So I think a few of you missed. I think Deepika, even you weren't there for
I missed the
uh,
last one.
our this thing. So today we are going to actually do two case studies on linear regression and logistic regression. Both will be done in R.
Okay.
So I mean, in case if you are not following it, uh, I think just revise the R lecture and I'll go
Okay.
through it step by step,
Okay. Okay. Thanks.
and then we will see how. I mean, when if it's again like the thing is right, like all the case studies are like just one or two lines where you need to call the models,
Okay.
but I guess like passing, how do you pass the variables to it, how do you load the modules and stuff is
Okay.
something which we need to like I'll go through that slow because we did how to like load data frames, how to load things from CSV and stuff last class in R.
Okay.
But today we'll be doing an application of it. So I guess like even if you're not following, I'll walk through the code step by step
Okay. Yeah.
to explain.
Thanks. That would
Some,
help.
yeah, yeah. So just so that everyone is on the same page. Today, what we'll do is we'll be using R for a couple of case studies. We did R last time where we actually saw the basic plotting, how do we load data into data frames, and how do we read from CSV files, web, and other stuff. So in case if you want to brush up, just go through the lecture recording from last class. Today, I think I'll focus first on the theory part, and I'll go through the, because I know everyone of you is new to R, so I'll go through the step-by-step method of how we are loading the data frame and stuff. I've sent the data sets to you guys. Please download them. Just download and keep them, and then once we do the R case study, we will like look into how do we go about handling them in a bit. But mostly, as I said, we will be doing in R Studio these last two case studies. So if you haven't installed R Studio, because if you didn't attend last class, please install R and R Studio. The links of both of them have been sent in the previous slides, but I'm hoping like uh, and worst come worst case, if you still haven't like started on R or haven't installed anything, I'll go through them step by step so that we can all be on the same page. So today, basically, the lecture is going to be on regression. So first and foremost, right, like we have dealt with until now most of the algorithms. In fact, not most, all of the algorithms we have dealt is basically classification. So what is classification, right? So classification is when you have some training data in which you have data and you have data labels. You are you and then you're given test data. You have to predict which class does that observation belong to. One example is, I'll refer back to Indian liver patients. So one observation is where you have the data from all the blood reports and stuff, and then ultimately you have a label in the end. If you have a label, that's called supervised machine learning. If you don't have a label, then it's called unsupervised. But in general, when you're trying to classify the test data, either you're saying that they belong to class 1 or class 2. So that is mostly the class, and 80% of the machine learning problems will fall under the classification problem. In classification, again, there are two types of classification: supervised learning and unsupervised learning. So supervised is when the labels are present to you. In unsupervised, when the labels are not present to you. In unsupervised, what we do is we plot the data in that n-dimensional space and try to see if we can make sense of the groups based on how they are arranged in that space. Let's say if all the class 1 is all clustered at one position and all the class 2 is clustered at another position, we try to form the groups by looking at the inherent nature of how they have been positioned in the n-dimensional space. But today, what we'll do is a different set of problems. Before I go into like linear regression, I want to talk about what regression is. So let's do a small comparison of what classification and what regression is, right? So basically, in classification, we are predicting a discrete set of values. What does that mean? given a set of measurements of a patient, if he has a disease or does not have a disease, given a handwritten number, identify if it is 1, 2, or 3. So these are all discrete values which we are predicting. Like has disease, does not have a disease is class label prediction. Given a handwritten digit, we are predicting one particular class. This written digit is 0, 1, 2, 3. So they're all discrete values. So usually classification is done by drawing decision boundaries, and all observations lying on one side of the boundary are classified as the same class. So this is pretty much like the last few classes with all decision trees, neural networks, support vector machines. We have done is basically this so far. So now let's look at what regression is. So ideally, so there are two main methods in machine learning. So regression, on the other hand, it predicts a continuous value. So the difference is when I said like regression is basically also, so it's a prediction problem where you are predicting one particular, one particular nature of a particular variable would take. Like for example, if you take the stock price, right? Stock price, it's basically, let's take Microsoft stock, right? It is varying between 100 to 110. So it's 100 and 110. So when I tell you like, oh, okay, predict the stock price of Microsoft 1 week from now. So it's not predicting a particular discrete value, right? It's not saying it's going to be high or low. So when you're predicting it's going to be high or low, it becomes a classification problem. But in regression, you're predicting the actual continuous value. So you will come up with a prediction and say, hey, I think depending on the data I've seen in the past couple of months, the exact value of the stock would be like maybe 105.85 or things like that. So when you're predicting a continuous value, or when you're predicting something which is not discrete in nature, you can also, there is another modification in regression where you predict discrete things too. But the idea here is we don't draw decision boundaries on and stuff like that. The way we solve regression is by fitting a model to the given data. So we have already seen when we talked about gradient descent, right? In gradient descent, we did an example where we actually had a line, and when we draw multiple lines to see which of the line gives the least error. If you remember the lecture, I showed you an image where we draw hundreds of lines, and then ultimately one line gave you the least error. So we use gradient descent to solve that. So regression is also kind of the same problem. We are not trying to draw decision boundaries. We are taking one particular uh, or one or multiple variables, and we try to fit a model given the training data. And when you actually present a test data, you're predicting the actual value. You're not predicting the class here. Is that clear? Is the difference between classification and regression clear? Like couple of examples for regression is, given the parameters of a house, the regression calculates the price of the house. Whereas in case of classification, this would be like, instead of predicting the exact value of the house, we will classify to say whether this house is affordable or not by certain person, right? So that becomes a classification problem when we are doing a two label problem. But here, when you're asked to predict the exact price of the house, that means that it is a regression problem. A regression problem basically means that you are predicting a value of continuous variable. So something, in fact, we did discrete variables and continuous variables in the previous class. Remember, discrete variables take precise numbers, like the number of baskets thrown by a basketball player. But whereas the height of all the people in the world, it's a continuous variable, or the temperature of on a given day, it's a continuous variable where you have float values, and it's not exactly discrete, but it can take any value which is a double or float in nature. One more example is, I've been giving this example always, like given the prediction of stock price, regression will give you an estimate of the exact stock price. So it's not a classification problem. Note that the house price and stock prices are continuous values. Is this slide clear? Like before I get into like linear regression, logistic regression, I think it's important to understand when to use regression and when to use classification. So in this regression problem, you basically, as I said, right, it's a continuous value prediction. Any questions on this? Any confusion between classification and regression?
No confusion.
Okay. So let me actually change this definition a bit. I think instead of saying predicting continuous values of a instead of saying predicting values of a continuous variable, I would say that in case of regression, you try to fit a model to the data given. Like if the data is like linear in nature, then you will try to fit a line for that particular value. If the data is polynomial in nature, like if it's like a zigzag or which looks like a sinusoidal wave, when you try to fit a model to the data itself, it becomes a regression problem. But whereas in case of classification, you're given multiple classes, you're not trying to fit the line to that particular data. You're trying to fit a line which separates both the data. That's the main difference. Like what if you actually mathematically look at it, in classification we are trying to draw a boundary between both the classes. That's the decision boundary. So when you are trying to draw a boundary between two classes, that becomes a classification problem. But when you're trying to draw the model of the data itself, it becomes a regression problem. I think that's a better way of understanding what regression is. So one of the simplest models is basically so there are three main regression models. We will do two of them today. So in general, there is something called as, so we'll be doing linear regression. There is logistic regression. We'll be doing that as well today. And then there is polynomial regression. So these are the standard regression models. So in linear regression, what we are saying is, given the data, we are assuming, so we don't know how the data behaves. Maybe we'll plot the data using, the plots and stuff, and then we will try to fit a linear line. So we fit a line through the data. That is the linear regression problem. In logistic regression, we'll talk about it in a bit. We fit a sinusoidal function. I'll talk about what sinusoidal function is. So logistic regression is used for categorical variables. Don't worry if you don't recollect what categorical variables are. But logistic regression is used when the data itself is not a continuous line, but when you have to predict whether, given a particular score, whether this cricket team will win the match or not. So that is a category, right? So category is whether win or lose. So this is a categorical problem in which you are not predicting the actual value, but you're predicting the outcome, which is a categorical value. Whether given a particular score, if a team will win the match or not win the match. It's again a two. If you look at it, it's a two-class classification problem, but you're trying to fit a model which will try to predict whether whether the match will result in a win or a loss, or one more case of regression problem is, given logistic regression is, given certain marks, is the person going to pass the exam or fail the exam? So we use logistic regression in such cases. Polynomial regression is if the data type is not, if the data is polynomial in nature, right? So instead of a linear line, I'll show you an example in R when we do the polynomial. If the data is polynomial in nature, where it's not a straight line, but it's actually a quadratic function or a parabola kind of a function, we generally use a like quadratic equation to fit that line. The main reason we are fitting this model to the data is to answer questions for the points which are not present. Like the case where I think we've done this quite often, right? So when we had, so let's say we have some points, right? We have like points, like different points. So let's say we have different points. Like in general, we'll see what the trend is. So this is your X, and this is your Y. So X can be anything, right? Like for example, uh, uh, like the price of the house, or let's say this is the stock market also, where X is the time and Y is your price. So when you have data like this, you'll first plot it, and then you will see that, okay, so these are the points given to me. The question asked to me is for any given point, can you answer the question? Let's say if I give you a X value, which is, let's say here, right? Let me use a different color. Maybe I'll ask for X value here, like this particular point. So do we have a value if we go up here? Maybe not, right? So we don't know what the value is because there's no point here. So in such cases, we use regression where we say that, hey, if the data is like this, I'm going to fit a model which will best represent the data. So let's say in this case, because it looks linear, I'm going to fit a linear line like this. So now I'll say that my model has learned the data which you have given to me. The reason I'm actually learning this line is, given any other value which is not part of my training data, I can answer and tell you what my predicted value of Y is. So in this case, I'm going to go here and I'm going to say the predicted value of Y is this. This is my Y value, Y dash. So given X dash, you can predict what Y dash is. So that's why we do a regression fit. One of the most simplest model is we assume that once you plot the data, we assume that it is a linear. It falls under the linear category, and then we say, okay, if it is looking linear, I will do a linear regression fit to explain the data. But what if my data is somewhat like this, right? So instead of having a linear this thing, so if I have my data which looks like this, let's say like this. In cases where the data does not look linear to you, so if this is the case, you can still, so the data given to you is this. It still looks, I mean, you can still fit a linear line, right? If you fit a linear line, it'll be like this, because it'll try to take all the data and try to fit a line which explains this model well. But you see, there's a lot of error in cases of, even the training error is really large. Like if you take any point X here, you're saying the Y value is here, but then it is like this. So if the data doesn't look linear to you, then we go for a polynomial fit. So the polynomial fit, in which case you will say, instead of saying when it is linear, you're actually saying y equals ax plus b, right? So that's a linear fit, ax plus b. But in case of a polynomial, you will say that I'm not going to fit a linear line, but I'm going to fit a line in which I'll say y equals ax squared, ax squared plus bx plus c. So you're trying to fit a polynomial line in this. If you actually solve for this equation using a polynomial fit, you can get a polynomial equation which is like this. So you'll try to fit a model which is like this. Explains the data much better. So first step is plot the data. That's why data visualization is the first thing we did in the class. Number one is like plot the data and understand how the data looks. If the data is linear in nature, go for linear regression. If the data is non-linear in nature, then you actually look for other kinds of things. We use either logistic regression or polynomial regression. We'll talk about logistic regression in a bit, but step number one, understand how your data is. So I'm not saying that you cannot do linear regression on data which looks like this. You can still do linear regression on this, but your error will be really high, because in linear regression you're restricted by using only ax plus b, right? So at the max you can draw a line like this or like this or like this. So it like if you're drawing a line which is like this one, then it doesn't perform well for this section of the data. If you're drawing a line which is like this, it does not perform well for this section of the data, because the data rate is really high. So step number one, understand what your data is. And if you feel that if you feel that a linear regression makes sense in this case, then go for linear regression. So, but then there are three main types of regression models. One is linear regression, logistic regression, and polynomial regression. So let's look at what are we trying to do here, right? So linear regression models involve one independent variables, which is x, which is a vector, dependent variable y, which is a scalar. Why do we say x is a vector and y is a scalar? Because x actually contains different features, right? So in case of linear regression, you're trying to predict y, which is a combination of different features. So when we say x is a vector, that means there is x1, x2, x3, x4 up to xn, where x1 to xn are features. So you're trying to predict the value of y uh, as a linear combination of this. So it will be a1 x1 plus a2 x2 plus a3 x3 plus an xn, so on, plus b. So that is basically, so in your linear regression model, the first thing you're trying to predict is basically a1, a2, a3, a4, so on up to an and b. So that's why they say x is, because x is basically features, right? They are independent of each other. But then y depends on what your x is, because y is something you're predicting. The unknown parameters b, they put like b is also a vector which contains a1, a2, a3, a4, so on up to b, explains the relationship between x and y, which is to be estimated. So therefore, the regression model is something like this: y equals some function of x and b, where f can be linear or non-linear. In case of polynomial, is f linear or non-linear? So when you're doing a polynomial regression, what is f? Is it a linear function or is it a non-linear function?
Non-linear.
It's non-linear, right? Because a polynomial fit is not a linear thing is anything in which x is maximum raised to the power 1. Anything which has x which is raised to the power 2 or 3 is becomes a non-linear function. So the whole regression modeling is kind of framed into this equation where y is a function of f of x and b, where x is your independent variables vector and b is your uh, b is the variables which you have to estimate such that it fits that particular model. So assume that the variable b is a vector of length k and we have n samples. There'll be three conditions. So this basically boils down to like linear algebra again, right? So let's say if you're saying that b is of length k and you have n samples, then if n is less than k, it becomes an underdetermined system. That means there's not enough data to find. Because I think all of you must have done this in high school, right? When I give you like uh, two variables to find and I give you one equation, can you find it? No, right? Because in order to solve for two variables, you need at least two equations to solve. Similarly, the problem here, when you don't have enough data points to solve for each individual variable, it becomes an undetermined system. If n equal to k, it becomes it is exactly linear. The system can be solved for a unique solution of b. When n is greater than k, which is most of the time, most of the time we have more data than what we have to predict, it becomes an overdetermined system. So that means that n minus k is usually uh, so these are the extra things, right? N minus k measurements is used to make a statistical prediction of unknown parameters. This excess information is referred to as degrees of freedom. You will see when we run the case study in R, you will see uh, when the degrees of freedom actually are are useful. So whenever, what are degrees of freedom? When you have more data than the number of variables you're trying to predict, it becomes it's called degrees of freedom. So in case if you have let's say I'm trying to predict let's say there are three observations, right? In three observations, then you will have three variables, a1 x1 plus a2 x2 plus a3 x3. Now let's say if I give you 10 observations, how many degrees of freedom do you have? So there are three features and 10 observations. How many degrees of freedom do you have?
4, right?
So how are you coming at 4?
Is it not n plus 1?
That is the number of variables you need to predict, right? Uh, so you're close, but you have 6 degrees of freedom. Degrees of freedom is basically the extra number of observations you have. So I'm just giving you 3 features, right? So the features are, let's say, square footage of the house, number of bedrooms, number of kitchens, right? And you have to predict the price. But then, so I'm telling you, use a linear equation to predict this. So what will you say? You'll say price equals A1 times the first feature, A2 times second feature, A3 times third feature plus B, right? So you'll have a intercept and you'll have coefficient for each feature. How many variables do you have now? 4 variables, right? A1, A2, A3, and B. So, but if I'm giving you 10 observations, right? So that means that for solving 4 unknown variables, you generally use 4 equations. But if I'm giving you 10 observations, that means you have 6 observations extra, right? Is that clear why the degrees of freedom is 6? Okay, let me ask a question the other way. So let's say, let's say I give you 3, so everyone knows the equation of a line, right? Y equals mx plus b. So this is the equation of a line. How many points do you need to solve to actually determine the equation of a line? So this is the standard coordinate geometry, right? How many
Two.
points do you need to solve
Two.
this equation? Why do you
Two.
need 2?
Because for a line to happen, you need 2 points to compare.
So that is that's a visual representation. But the reason you need 2 is because you have 2 unknowns. You have m and b. So let's say I give you 1 point. Let's say I give you 2 comma 2, right? So you will have one equation which will say 2 equals m times 2 plus b. You still can't solve it, right? Because you have, now there are 2 variables, but I have only one equation. But if I give you another point, which is say 3 comma 1, then you will be like, oh, 1 equals m times 3 plus b. Now you have 2 variables, 2 equations. You'll do the basic math, how to solve, these 2 things. You'll determine b, put it there, and you'll determine what m is. You'll determine this thing. So the standard rule in geometry is number of unknown equations. If there are number of unknown variables in an equation is 2, you will need at least 2 observations or 2 points. In this case, every point is observation, right? You need at least 2 points to solve it. But what if I give you 3 points? Then in that case, you can take any 2 of them to determine the equation of the line, right? Because if I give you 3 points, what if I give you 10 points? I'm telling you, okay, these are the 10 points in the line. Solve for it. That means that you are actually having 8 points extra. So this is called degrees of freedom. Degrees of freedom means that how many extra observations do you have to solve your equation. That comprises of degrees of freedom. Is that clear? Any questions on degrees of freedom? So the reason you have to understand this is, when you're doing the case study, you will actually see the term degrees of freedom and how the R module is playing with the degrees of freedom. But if you don't understand what degrees of freedom is, then you can't proceed further in the case study. So is that clear? Like, why did I say you have 6 degrees of freedom when you have 3 features? Because when you have 3 features, your linear equation becomes A1 times first feature, A2 times second feature, A3 times third feature plus B. So you have 4 unknown variables, and if I give you 10 observations, that means you have 6 observations extra, and that's the degrees of freedom for which you can play with. So having said that, let's see what linear regression is. So when f is a linear function, that means you're trying to model it as a1 x1 plus a2 x2 plus a3 x3, then it's called a linear regression function. One of the examples for that is this thing. So you have so graphically you have certain set of points. We try to approximate the whole data by plotting a straight line. So if you actually plot a straight line through it, then it becomes, so yellow line is what you are trying to come up with. But since that is linear, so the equation of the line is y equals ax plus b. But here, 1, 2, 3, 4, 5. How many degrees of freedom do you have here?
Is it 3?
You have 3 because you have 2 unknowns, but you have 3 additional points given to you. So there are some certain things which you need to understand is like, for example, this is a linear line, right? But the thing is, let's say, so this is an approximation of the data. Let's say you have a point here which has a value y, right? But what is the data predicting? For the same x, the data is not predicting this value, right? It is predicting that the value is at this line, y cap. So there is an error in your prediction. The error is y cap minus y. So the linear regression is still drawing a straight line, which is an approximation of this data. So it is saying that, hey, if you give me this x here, instead of predicting the value, if you give me an x here, instead of predicting this value, which it's ideally supposed to tell you, it is predicting a value which is here. It is still fine because overall it is trying to reduce the error. But for this point, it predicts an error of y cap minus y. So that is the error term. Is that clear? So actually, if you really observe, we have actually done linear regression when we did gradient descent. So in gradient descent, I don't know if you guys recollect that lecture. The first thing we said is, in order to actually optimize or fit something, we need something called as a cost function or an error function. And then we try to minimize that error function. That's why we did a partial differential of that error with respect to these unknown values a and b. So we try to minimize that error function to actually come up with, to actually predict these parameters. So that is what we did. We will see another method. Since we already talked about gradient descent, I'll talk about QR decomposition today. So you can solve the linear regression in multiple manners. The solving is basically the mathematical part. You can either use QR decomposition to solve it, or you can use gradient descent to solve it. Both of them will try to, but both of them are aimed at predicting the value of A and B such that the error when you actually predict a line through these points is minimal. So that is the main purpose of this solving these equations. So there are two methods. One, gradient descent. In gradient, both of them try to minimize this error, right? In gradient descent, what we do is we calculate the error for every point. For this particular point, error is 0 because it's exactly lying on the line. For this point, it is y cap minus y. For this point, it will be something else. It's this distance. For this, it's this distance. So we take the sum of all the errors and then we take a partial differential of that in terms of A and B to solve the equation for A and B. That is for if you're using gradient descent. But today I'll talk about another method called QR decomposition. Both of them are still aimed at solving the same problem. What is the best line you can fit through this such that the error in prediction is minimum? So there's one more line. I'll draw one line like this, just a vertical line. Is that having a better error or is this having a better error? So this line is what you have seen here. But what if I draw a line which is like, which is on top of this particular point, which is like this, right? Which is perpendicular to this particular line. If I draw a line which is perpendicular to this particular line like this, it will have a higher error, right? Because for every point, it is predicting some In fact, it's predicting some infinite value. For this point, it's not even predicting anything. So of all the lines which you draw, it tries to choose the line for which you have minimal error possible. So that is the goal. So let us see what is the criteria to fit to the line. In linear regression, the line can be, it can be any line that can be chosen by joining the leftmost and the rightmost point, by averaging the slopes of each pair of points and drawing a line with the average. So there are different methods. A line such that the sum of the error between the actual and the predicted value is minimal. A line such that the absolute value of the error between the actual and predicted values is minimal. So you can take different criteria to fit a line. So the main thing what we will do is we will actually take the line such that the sum of the errors between the actual and predicted value is minimal. So the last choice of fitting, what is the last choice? A line such that this is the one which will pick up. A line such that the sum of the square of errors between the actual and predicted values is minimal. So that's what I was saying, right? Because instead of one particular point, for every point we'll take the error, we'll square it, because we want the error to be, we don't want the error to be zero if it is plus and minus. Positive error and negative error is still error. So how do we get rid of that? We square the errors. So we choose a line such that the sum of the squared error between the actual and predicted values is minimal. So the last choice of fitting the line has the minimal value for which the squared errors between the actual and predicted values. This is called least mean squared error, or LMS algorithm. So you will see that most of the time when we talk of regression, they solve it using LMS algorithm. LMS stands for least mean square algorithm. In other words, linear regression is a model, and LMS is one of the methods to address this model. So there are other methods also. You can always say, I'll take 2 points and join the line, but that doesn't give you the least error between different terms. The other way to look at linear regression is that observations are assumed to be a result of random deviations from underlying relationship between dependent and independent values. So as I said, right, so you have different observations and you try to predict a line such that you, from the given set of observations, your error is minimal. So your squared error is going to be minimal. That will give you the best fit possible. So let's look at how this LMS algorithm is devised, right? So is everything clear up to this point? Like what LMS is, why did we choose LMS to solve this equation as opposed to other equations? Questions so far? Okay. So let's look at what least mean square algorithm is. In linear regression, we try to fit a line that approximates the points in a 2D space. That's what we've been talking, right? We try to fit a line which tries to approximate the points in 2D space. A straight line can be written as y equals ax plus b. Our aim is to estimate a and b given a set of x and y pairs. If your number of x and y pairs exceeds 2, then they are like the amount at which exceeds, it will be degrees of freedom. Once a and b are estimated, we calculate a value for a given xi may not be equivalent to yi, because that's true. Because when you actually come here, this point's value is not this, but it's going to be this, right? Because when you look at x here, we look at where the corresponding y is from that line. So that's a prediction value, right? So even though the point is here, we are predicting that the y value is going to be this much higher. So that error, so if you look at this thing, so once a and b are estimated, calculate the calculated value for a given xi may not be equivalent to yi. Let's call this yi prime. The difference between yi prime and yi is determined by the term ei. Note that ei can be positive, negative, or zero. So the way we actually determine the error equation is by summing up for all the points what yi prime minus y whole squared. The reason we are doing the whole squared is because we want the error to be, we don't want the error to be cancelled out. positive and negative errors are still errors. So we want to square them and add them. And what is yi prime? Yi prime is nothing but it is given from this equation, where once you determine what a and b are, yi prime is going to be a xi plus b, right? Because that's where your prediction is coming. So now once you have this above equation, this is called the cost function or the error function. The aim of least mean square is to minimize the above function to find suitable values of a and b. So if you remember gradient descent, we took this cost function and then we took the partial differential of that, and then we changed the values by certain delta, right? We did minus eta times the gradient of this particular error function with respect to a and this particular error function with respect to b. So we changed the a parameter with a certain learning rate depending on the slope. So that is one way of solving it. So since we have already discussed that way, in this lecture I'm going to talk about how to use QR decomposition. It's a matrix technique to solve this particular equation. So assumptions in linear regression are independent variables are assumed to be error free. Like for example, if you get each feature variable, so there is no error coming from how you're measuring each of the feature uh, in your uh, in your data, right? So independent variables are assumed to be error free. The variance of the predicted dependent value y have the same variance of their errors regardless of the values of independent variables. So what that means is, because the independent variables don't have any error in measuring, the variance which you have from the dependent variables in y will have the same variance which comes from the error, right? Because if your measurements don't have any errors, the variance you get in y is because of the variance in the error. So they have like different terminology. It's called this thing, I don't even know how to say it. It's called homocedasticity. If you hear this term, then you basically it means that that is an assumption in linear regression, that the variance which is coming from the predicted dependent variable is coming from error. That assumption is called this thing. The columns of the independent variables are linearly independent. So this is the thing I've been emphasizing from the first lecture onwards. How do you choose features? What is our main criteria to choosing features? We need to choose features such that they're independent of each other. Even if there is some correlation between two feature vectors, that means that your data is being impure. Like that means that you're feeding the machine certain feature variables which actually have some dependencies on each other. If that is the case, then you're confusing the data. Always choose features such that they have high variance, and second thing is they should be independent of each other. So we will see how R will tell us that. So when we do the case study in R, it will actually tell you like these variables are not independent of each other, please replace them. So so yeah, one of the criteria is all the columns or features are independent variables, or they are of independent variables are linearly independent. So they have to be linearly independent. This is known as lack of perfect multi-core linearity. So collinearity means what? If you have two variables, they're said to be collinear. That means if one is increasing, the other is increasing. So if they're independent of each other, then you will see that if they're random in nature. So I think I'll just show you an example so this is the case study with the biking data, which we will do. Before we get into that, I want to show you like how this collinearity is determined. So this is the biking data set, right? So let me just run up to, so one cool thing in R I showed last time is the fact that you can run them from the middle of the code as well here. So like when we'll do the case study, you'll understand this better. But what I did here is I did a scatter plot of each of the variable which I considered for the biking data. So the biking data set which we have in today's class, it actually has different parameters like temperature, humidity, wind speed, and stuff like that. So depending on the problem which we have is we need to predict the number of bicycles that store needs to stock up for tomorrow or day after tomorrow. The features which that store gave us is basically the temperature, humidity, wind speed of that particular day. So given these features, can we actually say something about uh, the number of bikes they need to store? But if you actually look at this thing, so this is like a plot where this is a plot between uh, temperature and a temp is another feature of temperature which we have. Obviously both of them are related, so you see they're collinear with each other. But whereas if you take temperature and humidity, the plot is like garbled and jumbled, right? And if you take temperature and wind speed, they're also jumbled. So that means that if you're choosing temperature, don't choose a temp. You choose temperature, humidity, and wind speed, or choose a temp, humidity, and wind speed, because these two are collinear with each other. It'll it will affect your assumption that this particular thing are linearly independent of each other. The assumption in linear regression is the features should be linearly independent. So this is called lack of perfect multilinear collinearity. Mathematically, the rank of matrix X should be full rank, which means that we've seen this in the previous lectures too, right? Because if the rank is not equal to the number of dimensions, then there are certain parameters, then there are certain features which are dependent on each other. If the rank is not full, linearly dependent columns need to be dropped from the model. And we will see how the case study in R will tell us that. So just let's just finish the theory part of it, then it'll be interesting to see the case study. Then there are other things here. So this is important because sometimes okay, let me open up did all of you download the data sets I sent? Yeah.
Yeah.
Yeah. If not, please download it at this particular point of time, because we'll be talking about uh, how do we fit linear regression models given the data. So let me open the biking data. So let's open README. So the README. So this is actually. This data was part of this paper. It was produced by Artificial Intelligence and Decision Support Laboratory. So if you look at this thing, this is the background of the data we are using. So bike sharing systems are a new generation of traditional bike rentals, where the whole process of membership, rental, and return. I mean, you can read through this yourself, but the main crux of this particular data is there is a company, New York bike rental company, where they're trying to promote using bikes instead of using cars to people. The problem is the problem they had was basically uh, some days they used to have more customers and they used to not have enough bikes. So and then other days they had more bikes and they had less number of customers, based on then they had to pay more cost for storing those bikes. If you have more bikes and no customers, you pay more cost for storing those bikes. So the problem which they gave was, so they gave this data set in which they actually taught all the features which can affect this particular number of bikes they need to store. So they gave like environmental features like weather conditions, precipitation, which day of the week, which season, which hour of the day, etc., which can affect the rental behaviors. The core data is related. So we actually got this data from this website. It's actually true real world data. It's not made up. And we got the data for 2 years. So if you look at our data set here, let me open the day. So if you look at the data set here, so this is the ID, but it'll tell you which day, what season it is, which year it is. Like, I mean, they next year is labeled as 1, 2, 3, which month, whether it's a holiday or not, whether it's a weekday or not, whether it's a working day, what is a weather condition, what is a temperature. You can go read what a temp means. I'm not 100% sure. I think it's another metric of temperature, what humidity is, what wind speed is, and these are the number of, this is what we need to predict, the count of the number of people who come for the bike. So this is what we'll use a linear regression model for using all these parameters to predict the number of bikes. So this is a regression problem. But the problem, do you see anything with this data? Like different, you have different features. Do you observe anything different, or anything which you feel is weird? Not weird. I wouldn't. Sorry, maybe weird is not the right term. But I see like two patterns of features here. Do you have any questions on them, or like do you see anything different between the features we are using? Can all of you see my screen, right? Do you guys see anything different in the data? How many of you have downloaded this data?
I've downloaded it.
So, alright, if so the main thing I was trying to get at here is, so this is still fine, right? Like these are the continuous values where you are actually trying to predict the outcome using these continuous values. But what will you do with these values? They are not continuous. They are actually telling you which day of the week, which I mean, which day of the week you're using, which month it is. So this is basically, so these are called factor variables, or they're discrete variables. So the thing is, you can do regression even using discrete variables. So these are continuous variables because the data is actually continuous in nature, where you can have any value in the float. And these values are basically discrete in nature, or they are called factor variables. So we will see how we can use factor variables and continuous variables to predict how many bikes on a given day should that rental place be storing, so that they can optimize their performance. So let's continue with this thing. So there are two kinds of variables. The reason we want to cover this is because most of the time when you're doing linear regression or in general regression problems, you will see features which are both continuous and discrete. And we will see when we do the case study in R, how do we actually tackle this problem? How do we tackle the problem that if the data is continuous and discrete in nature, how is it that we'll fit the model to it? So let's see what discrete and continuous variables are. So the observations or independent variables. So observation is basically nothing but our features, right? Or the independent variables can contain both continuous and discrete variables. For example, if one of the feature is temperature in Celsius, it's a continuous variable. The temperature value can be substituted in the formula as it is. If one of the feature is indicating whether the day is a working day or a holiday, which is 1 for a working day and 0 for a holiday, these are discrete variables. So the same days of the week or the same days of the month. So all these are discrete variables. While fitting linear regression, these need to be treated differently because since they're not continuous, right? How will you actually predict something when I give you just two values? So I'll actually show you we'll do a step by step. So I'll do one case study with continuous. I'll do one case study with exactly discrete values, and then we will do a case study which has both mixture. The biking data set has a mixture of both of them, both continuous and discrete values. So while using R or Python, one has to mention separately the discrete values. In R, they're called factor variables. In Python, they're called categorical values. So remember, we actually, when we were doing uh, the exercise in Indian liver patients, we had the gender. The gender was male or female. So we actually had a function called as categorical, which actually converted them into numbers, right? So in R, they're called as factor variables. A factor or categorical variables are further divided into cardinal or ordinal variables, which we need not worry about now. The R function will take care of it. A cardinal variable is a variable whose values can be ordered. For example, movie ratings are cardinal variables. A 5-star rating is much better than 1-star rating, but it is not quantifiable in such a way that the former is 5 times better than the later. So these are a cardinal variable where you can actually put them in some order, but it does not actually mean that they're 5 times better, right? Like there's no particular quantity metric to say that. Ordinary variable is a variable which cannot be ordered. For example, days of the week, months of a year, male, female, there's no order to it. But whereas cardinal variables, you can actually say, like, you can order them in descending or ascending order. So these are just terminologies, but it's important to know that when you're looking at the data, like for example, the bike share data, you will see that there are both they are both factor variables and continuous variables. So we'll see how do we do a linear regression model for this thing. But before we go into that, let us finish off with the theory here. All right. So I told you there are two ways to actually solve a linear regression problem, right? So one is using gradient descent with optimizing the cost function or error function. The other method is basically called QR decomposition. So let's see how we solve it. So solving for linear regression equation. So by the way, this is how our library does this behind the scenes. So I'm just giving you an example or the math behind it such that you understand how it's solving it. So as stated earlier, a linear regression equation is y equals w transpose plus b. So you can always make it into matrix, right? Like we saw this from like the second and third lecture. You can always put all the unknowns into this matrix W, and then you can multiply it with the vector X. So you can always express Y as W transpose times X, where W contains the coefficients of each X vector, right? So A1, A2, A3, and B can all be put into this matrix called W transpose, where and then you can express the equation as Y equals W transpose times X. This can be solved by matrix methods or numerical methods. Matrix methods, we use a technique called as QR decomposition. In numerical method, we use gradient descent. So since we have already covered gradient descent in when we did the class on gradient descent, today I'm going to show you QR decomposition, how to solve this using QR decomposition. The main thing both these methods solve is they try to find the optimal set of these parameters A1, A2, A3, or this optimal set of W transpose such that you get the actual fit which has the least error to it. So in case of biking data also, we'll see how that is being done. So let's see what is QR decomposition. So QR decomposition is basically, if you've followed the lecture on eigenvalues and eigenvectors, I'd actually said that a matrix can be decomposed using SVD decomposition. I don't know if you remember that from that lecture, but using SVD decomposition, we took a matrix and divided them into U, sigma, and V transpose, right? Where sigma contained all the eigenvalues and then U and V were the eigenvectors. So similar to that, there is this is how we do QR decomposition. QR decomposition means that any matrix which can be expressed and in terms of Q and R, where R is an upper triangular matrix
and then Q is so here Q is an orthogonal matrix and R is an upper triangular matrix. So this is a decomposition of that matrix. The reason we do that is, look at this thing. So the equation we have is X times W equals Y. If we multiply both sides with X transpose, it becomes X transpose X times W equals X transpose times Y. So if we can actually decompose X into Q and R matrices, it becomes QR transpose QR times W equals QR transpose times Y. And then if you open the transpose, it becomes R transpose Q transpose this thing. So since Q is an orthogonal matrix, Q transpose times Q becomes identity matrix, right? Because it's an orthogonal. Orthogonal means that when you multiply the matrix with the same thing, it becomes 1. So in this case, it will basically become R transpose times R times W equals R transpose Q transpose Y. You can, if you cancel R transpose on both sides, now it becomes a simple equation where R W equals Q transpose Y. Since R is an upper triangular matrix, the last row will only contain one term, which can easily be found. So the reason we did this is because matrix inverse is really difficult operation to find, right? So that's why they do QR decomposition to find out what W is. So what they'll do is, since R is upper triangular matrix, it becomes very easy to solve this equation, and therefore you get what W values are. So that is basically how. So you need not worry about what this does. The module will take care of that for you, but you should know how the module actually runs this QR decomposition. Any questions on QR decomposition or how we try to find the unknown values? Are you guys following what QR decomposition is and why are we doing QR decomposition? Why not gradient descent? Deepika, do you have any questions on QR decomposition? Satya, what about you?
No questions.
All right, so we have this QR decomposition method, which is another way of solving the unknown variables A1, A2, A3 using just the matrices. One other method is gradient descent, which we actually saw in the previous class on how to solve that. But QR decomposition is another useful technique, which I think R uses to solve for the unknown variables, which we have A1, A2, A3, so forth. So once we have the QR decomposition, so let's see how linear regression is done in R. So linear regression is in R is solved by using the function LM. So when you open R, so actually quickly open, let's do a simple fit. So quickly open this. So there is one file which I sent, which is a CSV file called one dimensional no noise.csv. So let us actually plot them. So how do we do that? First, we actually do, we set the working directory to wherever you have put the CSV file. So the first command is set working directory. And then we actually read the CSV file. So reading CSV file, we actually saw last time where you said read.csv, you read the CSV into your variable. And then this is, when you read the CSV, it becomes a data frame, right? But in data frame, you have whatever you've given. So if you open one dimensional data,
So I'm actually asking you to plot using one-dimensional, no noise. If you look at this, you have an X and Y value in this thing. So your X and Y is here. So your data will actually have the first row will be treated as columns in which you have X and then you have Y. So when you actually load this particular data frame into X and Y, the way you access each column is by giving $X and $Y. So when you read, so if you are actually like loading the data, all I'm saying is like when to do a linear fit, we actually first need to load the data from the CSV and it's stored in this value XY. So in XY, if you do dollar, so it'll give you the prompt. So dollar is how you access each column. So in R, in Python, we use square braces and put the name, right? But if you do use dollar, you will actually access each column. So, and then so this is the data. I just did a plot. So if I just run this, so it's basically just a linear data. So the function is very simple. It's called LM. So LM is basically the linear module. So this is what is linear regression fit. So in linear regression fit, you use the function LM to actually plot your data between X and Y values. How do we do that? So the function for linear regression is going to be like this. LM, linear module. You basically take your data frame which you have loaded, which is Y. So this symbol tilde means versus. So you have the thing is when you're using LM, it is Y versus X, right? Because you want to plot the correlation between Y and X, right? So the way you do it is basically you first load Y here. So LM of XY is where I've loaded my data, $Y, and then we use tilde, and then you give XY $X. So this will fit that model for you. So the model, after it fits that model, I've stored it in LMXY. And then when you do summary of LMXY, it'll tell you, if I do summary of LMXY, it'll tell you how that model has been fit. So let me run this. So this is the summary of LMXY. So in LMXY, it'll tell you, so there are a couple of things here which are really interesting. So it'll tell you what the residual score is. So if you fit it, you see the residual score is really minimal here. It's 10 to the power of minus 14. So that means that because the line is, this is the data, right? It's actually a straight line. I've actually given, without noise, I put this data here. So when I actually plot it and I use the summary of Y and X, you will see that basically it predicts the coefficients. So you want to predict what A and B are, right? So it predicts what the intercept is, it predicts the other coefficients. So this is basically what your linear regression model fits, the estimate here. So it predicts what the intercept is, it predicts what your A coefficient is. There's something called as p-value. P-value means the lower the p-value, that means the higher the confidence. So you see that the p-value here is 10 to the power of minus 16. That means it's really confident in this particular metric. And there's something else you have to observe here. You have these 3 stars next to the prediction. That means that if it has 3 stars, that means that your intercept and your initial variable have higher confidence. 3 star means it's around 99.99% confident that these two things are useful for your regression problem. If it is 2 stars, that means it is 99.99. If it is 1 star, then it is 99.95. If it's only a dot, it means it is 19. It means only it's 99% probable. So if you have 3 stars, that means that these two things can be used. But when I actually use this on my bike data problem, you will see that not all of the features which you are using are useful for the prediction because they are not linearly independent, right? So this is one method you can use to actually throw out the features which are not linearly independent of each other. So if they're linearly dependent, the stars will tell you how confident is the model in predicting your values. So this is like the basic linear regression model. So all you need to do is just fit LM between Y and X, and then just do the summary. It'll tell you like what are the predicted values, and then you can actually use this model to plot it. So AB line is the command to actually draw a line through the data. In AB line, if you pass the model and give the color, so let's run this. So you see, it actually drew a blue line through this data. So that's how you can actually use linear regression in R. But this is the data which is really simple to plot. But as we go further, I'll show you how to use the biking data to predict. Can you guys actually quickly code this? So this is the, and you can get the coefficients also what it has predicted. LMXY coefficients of 2 and LMXY coefficient of 1. So that will tell you what A value is, what will tell you what B value is. Do you guys think you can write this program in R? Or should
Yeah.
All right.
Is it possible to zoom in a little bit?
Oh, sure. Zoom codes. Maybe view. Yeah, zoom. Is this better? Or let me zoom in again.
Yeah, that's better.
So the way we are using linear regression is the first data set which we have is one-dimensional data noise. We are just reading the CSV into X and Y, and we are plotting X and Y. So that's just the basic plot. But then if you want to fit a linear regression model, you use this module called LM, and then you give Y versus what are the variables. So Y versus X, and then you take the summary of it, will tell you like, so the summary is really useful. So the summary, this is the summary in general. So the summary will tell you what is the coefficient it has predicted. And you see the p-value here. This section p-value is the one which tells you whether to use that thing for prediction or not. So it is the 3 stars means it is 99.99% confident that these two features are really fit well. As you can see, right, the error is like minimal because it's the straight line which has gone through like all these points. So, and then there's something called as R squared error. The higher the R squared, the better is your result. So these are the parameters which you need to see. When we predict it with the bike data, you will see that it will tell you which parameters to use and which parameters not to use also. So you need not worry about, oh, whether all my features are linearly independent or not, whether they are dependent on each other or not. So the R algorithm will automatically tell you how to do that. So Satya, bear with me 1 minute. Let me just finish off the other section for linear regression. Then we will go and like do the basic code in R. And then we will start with the biking rental example. So in R, linear regression is solved using the function called LM. LM is used to fit linear models. It can be used to carry out regression. So what it does is it does an analysis of variance and analysis of covariance. The reason it does this is to find out which features are linearly independent and which features are dependent on each other. This is the usage of it, like how, and we will do this when we actually write the code. We are going to use this particular formula. So here is the important thing, right? What will it give you? It'll give you all the coefficients. It'll give you the residuals. What is a residual? Residual is nothing but your error. So if you look at the R prediction here, so it'll tell you what is your residual score. So your residual is 10 to the power of minus 14. So residual is nothing but the difference between your actual value and the predicted value. That's your residual score. So the summary analysis is really useful to predict that. So it uses residuals, and then you get the mean value of it. It tells you the rank of the matrix and so many other things. So the model itself will guide you in the right manner to say, hey, use these features, don't use these features, to get better accuracy and stuff. So quickly, before we go into the case study, the pros and cons of linear regression, right? Pros, it's very easy to use. The derivative model uses very basic maths, so it's easy to understand. Cons is if the relationship between dependent and independent variables is not linear. In most of the practical cases, it is not linear. So then you will have more error. It is also affected by outliers in Y. So if you have like a data which is not linear in nature, or which has a combination of both categorical and continuous variables, then it's not a good method to fit. So having said that, I think we did the basic theory about like how linear regression uh, is used. So couple of things, we can do linear regression by using gradient descent or using QR decomposition, but both of them are done by this library here called LM. If you use LM module, you can directly I think it uses QR decomposition to find out what your models are. Let's actually quickly write the basic analysis. So there's one file called one dimensional no noise.csv. I want you to write this code so that you understand how the data is like loaded into your so when you do read CSV, you actually get a data frame, and then you can access each column of the data frame by using the $sign, and then you can use LM of Y versus X. That will give you the model. You can do the summary. The summary will tell you which features to use, how confident it is for every feature. In this case, it'll tell you the intercept is 3-star, and then this value of X which it is used is 2-star. Is also 3-star. That means 99% confident. P value, the lower the P value, the better is your model fit. Higher the R squared, like 1 means the highest. So this is a perfectly, as you can see, I've given it points from the same line, so that's why it's the best fit model. And then you can print out what is the X and Y coefficients there. You can print out the differences also, like what the predicted. Most of them will be 0. So let's quickly write this part, and then the next parts I will explain to you, like how do we do it for the biking data. The only difference in the biking data is it's not just continuous values, but you even have discrete values. So I'll show you how to actually handle discrete values along with continuous values in case of biking data. Can you see the code, Satya? Like, or do we need to zoom in again?
Yeah, that's better. I can see now.
Okay. So the main analysis of the thing is done by this section here, the summary. So once you fit a model, the summary of the model will tell you a lot of things. And in case of biking data, when we do that example, we will see how it is telling which variables to use and which variables not to use. So while you're coding, I will give you so this is the basic of linear regression, what we fit. So as I told you, we'll go step by step. First, we'll fit a really good line, which doesn't have much noise. Then I'll take some noise and plot and do linear regression on that. Then I'll take one case study which only has categorical data, or in case of this thing, it's called factor variables, which only has factor variables or categorical variables. And then we'll go into the biking data case study. So this is a simple line where we have plotted it with no noise. I can repeat the same thing with noise also. So in this case, I've done it without noise. So let me actually quickly run it with noise. So it's the same 4 lines I've done again. So let me run this. So you see here, if it has noise, then you will see that it's not perfectly a straight line. But then the cool thing to observe here is you will actually see when I did the summary on this, the residual scores are no longer 0, because there is a difference between what you have captured here and what your line is. So the residual scores are no longer 0. So you have some residual score, but it still has a low p value because it's still fitting the line well, right, to this particular data. It has the intercept estimate of this and A estimate of this thing. And as you can see, I think your R value is no longer 1. Oh, R value is also. So this is. Let me just stop at summary so that we have. This is one dimensional with noise. So let me just run this back. See, your R value is no longer 1, but it's very close to 1. So the higher the R value, the better is your model. And it is telling you that both of them have high confidence. It has 3 stars for both of them. So that means you don't need to remove any parameters or any function. In this case, there's only one feature anyways, so it gives you both of them. And after doing that, if you see, you can actually plot the line also. So if I run this, see, it plots the line. So I'll give you like 2 minutes to, you can do it on, you can load whichever data you want. You can load one-dimensional noise.csv, or you can load one-dimensional no noise.csv as well. So depending on whichever data you want to actually load and run it, you can run it and do it. Any questions on how to run linear regression in R? I'll wait for you to finish this, Satya, and then we'll go ahead and I'll show you how to run it on factor variables and categorical variables. Then we will use the biking data example, because the biking data has a lot of values which it gives us humidity, it gives us wind speed, it gives us it gives us like a lot of temperature, and whether it's a holiday or it's a working day, whether it is, so as we can see the biking data here, it gives us a lot of these things. So then we will run an algorithm to you. So this is very interesting data set, because not all of them are useful in your prediction results. So all the summary things I've been talking here, where you have the R squared, p values, and the star metrics here, they will be different. So when they are different, you actually then go back and then remove those things from your training model, and then you will see that the improvement happens automatically. So let me know once you're done with this basic thing, then we'll go into the details further.
Sorry, I joined a little bit late.
Okay, Jatin. So basically we are doing linear regression and logistic regression today in R, but we'll be mostly done with linear regression with biking case study in the next 15 minutes. So we have another new topic, which is logistic regression.
Okay.
So you can follow along with it. But this is basically the 4 lines of the code, how you actually do linear regression. So linear regression is nothing but, given the data, how do you fit a linear line through it? The reason we do that is, in case we get some new values, we have to find what the predicted value of y is. So this is generally used for, like, if you want to use like for predicting stock market values or something, right? And so basically in stock market we use polynomial regression because it doesn't follow a linear pattern in general, but basically we use regression to fit the data, fit a line, or fit a model to the data, such that when you actually are given values which you have not seen in the training, you can actually find out what the value of that is. Like for example, in the stock market, right? Let's say I give you last 2 years worth of data and I tell you, can you predict what is the stock going to open on Monday?
So what you'll do is you'll take all the data, try to fit a polynomial or a linear graph, and then use that to explain or to predict what the value is uh, on a future day, because you already fit a model to it. In this case, I'm fitting a linear model, so it's a linear. It's called linear regression. So in this case, let's say if I give you 110, so you'll actually go here and then say, okay, it is somewhere around 220. So that's what we've been trying to do here.
I finished.
You finished? So did you get the plot?
Yeah.
Okay. So once you got the plot, like there are like these coefficients also which you can print out, like what it has predicted and stuff.
Mhm.
So this is with a simple example with noise. So there's another case study which I actually. So this is something. So this is the one with noise, right? So let me actually. So the next one is. So as I said, right, you. Oh, so the next section of the code, we are using another data set for nonlinear data. So in this case, what we do is we are reading a file in which the data is nonlinear, and then we try to fit a linear line through it. So let's see how does that work. So even if it is nonlinear, so I said you can select something and do Control Enter, right? So in this case, a polynomial fit is a better fit because you see the data is actually just not a straight line, but it is actually following a polynomial pattern. But still, if you fit a linear regression model, you'll see that it fits it like this. So now let's look at the summary here. So the summary in this case will be interesting. So if you look at the summary in this case, see the R squared is still, it has become low. It's not 9.95, it's become 0.93. And look at the other parameters here. So the p-value is also not that low anymore. It's 10 to the power of, it used to be 10 to the power of minus 16, and now it has become this thing. Residual also has actually increased. Residual is nothing but the sum of errors for each of the points. So the residual here is minus 133. So you see that parameters have changed. So then it will tell you that, hey, instead of using linear fit, try to use a polynomial fit. Then the next kind of thing, before going into the bike rental example, I want to show you one fit which uses only factor variables or categorical variables. So if you look at this data set which we have, two-dimensional factor variable. So as I told you before, what are factor variables? Factor variables are the ones which have not continuous data. So you see this thing. So there's a factor variable A, and then there is a factor variable B. So A and B, so this is factor variable means discrete values, right? So this only has a value between A and B. And the next factor variable FAB of B is 1 and 2. And then the Y is basically what we are predicting here is basically a continuous variable. So this is interesting because factor variables, if you have continuous data, we can fit lines, right? But if you have factor variables or categorical variables, it's really difficult to fit lines. So what we do in case of such things is basically there is this function called, you actually modify it, called as dot factor. So when you give it as dot factor, so it's the same thing in Python when we did as categorical. Remember when we had a gender and we had male and female as two categories, we actually converted them from categorical variables into numerical variables, right? So similarly, we do the same thing for in R. We call it like as dot factor. So in this case, let's just do one thing at a time. So first, let's read the categorical variable data. Oh no, this is one dimension. Where is categorical variable? Using factor variables. So okay, this is one dimensional factor variable. So let's see. Let's do this. So the first thing I did it with is with only one dimensional categorical variable.
This is two-dimensional categorical variable. There's another thing called one-dimensional categorical variable. So in this case, so it has the number of shoppers and it tells you whether it is a weekday or a working day. So if it is 0, that means that it is basically a holiday. If it is 1, that means it is a working day. So let's see, in this case, your X is categorical, right? Because it's not continuous, but your shoppers are pretty much continuous. So let's see how the linear regression behaves in this case. So when I load the data here for the shoppers data set, so let me load the data. So I load the one-dimensional data and let me plot it first. So you see here, either the value is 0 or it is 1. So the values in between, they don't exist because it's a categorical variable. So in such cases, when you do, the way you do actually linear prediction is basically by giving these things, but you actually typecast it by calling dot factor. So you convert the working day into a factor variable and then you actually look at the result. So let's do a linear regression fit for this. So you check to see what the data point is. Let me do a linear regression fit. This is how it predicts it. What does this tell us, right? So this tells us, like, if at all, so this is the number of shoppers on a holiday. This is the number of shoppers on a weekday. So the linear regression, when I try to plot a line between these two, it actually runs through the mean of both of them, which kind of makes sense, right? Because let's say if I give you the number of shoppers on a holiday and I don't give you anything else, I don't give you Monday, Tuesday, this thing, I just give you holiday on a weekday. And then I tell linear regression, hey, linear regression, please fit a line for me given these two values. What will it do? It will plot the line between the mean of the first categorical variable and the second categorical. The first value of the categorical variable and second value of the categorical variable. So that's how linear regression looks for categorical. Until now, we have seen the linear regression for continuous values. If you give discrete value, it kind of looks like this. So it passes through the mean of both of them. So that's how we actually, and that's how we understand what linear regression for discrete variables looks like. So let us actually go ahead and then see. So this is how the distribution is. And if you go back to the previous plot, we actually saw that the line runs through 78 and then the other line runs to 25, right? So this is the box plot for each of the line. And then when we do a linear regression for categorical or factor variables, it's the same thing. Categorical, or in R, we call them factor variables. In Python, we call them categorical variables. If we run it for these things, it will pass through the mean of both of them. So, yeah. So it fits the line and then see how it works. So is this clear? If it is a factor variable, how does the linear regression look? So since this is done, now let us look at our biking data. So as I was telling before, the biking data set is actually, if you read the README file for it, it's actually published in this paper, and it is actually it's got from the government of New York, where they were trying to promote people to use bike rentals instead of using cars. The problem they faced there was they did not know how many bikes to keep in their rental place, because it kind of varied. The demand kind of varied depending on the weather conditions, season, environment, work, which day of the week, which hour of the week, etc. So that if you look at the bike rental data, you can actually see that these are all the observations which they gave, and this is the final count which we need to predict. So the date, season, year, month, holiday, weekday, what is the temperature on that day, what is the humidity on that day, what is the wind speed on that day. The first things we need to use for linear regression is we need to find which features to use. And what is the first step in actually using knowing which features to use? Like, is there a criteria for how do we choose features? This is like, I think we have discussed this a lot of times in the class. How do we choose which features to use? So we have all these features, right? Season, holiday, blah, 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 blah. What is the first criteria to know which features to choose to give it to our model? So we have discussed this a lot of times, right? Like, how do we know which features to pick?
Features which don't overlap each other.
Yes, features which are independent of each other. So that is the first. So in feature engineering, we did a lot of work to see which features are the ones which don't, which are independent of each other, which don't have any covariance or correlation with each other. Because if you're using features which have linear dependency, that means you are confusing the system by giving the same thing in two different features. So how do we find that? So R actually will tell us, R is actually a really powerful tool to tell us which features to use and which to not use. So first and foremost, we need to do data pre-processing. So let me first read the data. So I'm reading the data in this case, read. So I'm here, right? I'm reading the CSV. Then I actually print out what, so these are all my features. So str of the features will tell you, it'll give you a description of number of columns, what are the unique set of values and stuff. From this, you can see that these are all categorical values, right? They don't actually, they're not continuous in nature. First step, what we do is we take these values and then we do as dot factor. Whenever they are categorical variables, that's the data pre-processing which we need to do. Even in Python, we did this. If you remember, we did dot categorical. So it'll create categories for like things which are male, female, and stuff like that. So first step is data pre-processing. We go ahead, get the Y count. We actually go and like all the categorical variables, we type them as factors. So look at this thing, right? So in general, when you're doing LM, you're taking Y, and when you give a dot, that means you're taking all the features to fit for that particular model. You can actually do, if you want to remove certain features, right? So how do we do that? We do dot minus, you can pick one feature. Like for example, if you don't want season, right? So you can just say bike data minus season. So that means you're taking all the values but this value. So this is how you delete the feature. If you don't want all the features, you do dot minus that particular feature. So if you subtract that particular feature from the dot, then it will take all the features but that value. But today we will actually see, I'll try to plot it with all the features and show you why it is really bad. And then we will use the summary key in the data set to remove some features. So once we have actually finished category, the pre-processing step here, so let me fit the model here and let's look at the summary of this. Look at the summary when I used all these features. So remember in the previous cases when I showed you, all of them had 3 stars. But look at this thing. So it is actually now, why do we have season 2, 3, and 4? That's because season is a factor variable and it has like, the value is 2, 3, and 4. It has 4 different categories. That's why it treats each of them as individual metric. There are holiday actually has only 1. Weekday has 1, 2, 3, 4, 5, 6. That's correct, right? Because there are like, Monday, Tuesday, Wednesday, Thursday, Friday, and weekend. So that's why it actually creates 6 categories for them. But if you look at this here, only some of them have 3 stars and some of them have 1 star. Some of them don't even have any values. So that tells us that not all of them are there. Look at the R squared value is way less. Remember when we fit for standard noise values, it was around 0.9596, right? Now all of them are really less. P value is also less, but then it is not as low as what the previous ones had. So this tells us that, hey, these particular, like, don't use these features. If you remove these features, that means there is some interdependency between these feature sets. Only use the ones which have like high confidence in them. 3-star means it is 99.99% confident that this particular data is useful. Dot means 99.05. If there is nothing, then it's not at all confident. So it is giving us a first hint that please
see that not all the features in this are useful. So sometimes it is we remove that feature and then we train again. So now let us actually go ahead and then remove some of these features. So once we did that, so now we understood that not all features need to be useful, right? So let us take a look at the data and see why is it saying so. Is there something which are dependent on each other or not? So for that I use like scatter plots again. To the way we do scatter plots in this thing is called, there's a function called pairs. In pairs I've actually plotted these 4 metrics to see if there is any relationship. If there's linear relationship, that means they're linearly dependent on each other, right? So let's look at this. Here we go. This is the graph I was showing to you before. So between temp and atemp, there is a linear relationship. Between temp and humidity and wind speed, look at all these things. These means that they both are not related. Basically, temp and atemp, they have a linear relationship. So if they're linear relationship, we need to avoid one of them. So that's something which we need to remove. So look at this. Note there is linear relationship. There's no relationship everywhere, but except for temp and atemp. So in our model, what we will do is we will avoid one of these. We'll not fit the data using temp and atemp. So the exercise to you is fit the data but remove atemp. So take this and then you just say dot minus. You take all these things but atemp, and then fit it again and see how better is your result. So that is the assignment for you. So I'm taking this value, pasting it, but I'm removing atemp because we don't want to use it because it shares a linear relationship with something else. And then once you train it again, so let me do this. I'm going to remove atemp and I train it again. So now I will see, you see that it'll have better results here. It still says that some of them you should remove, but in general, the R squared value slightly improved from 0.53 to 0.55. So that's how you basically do the analysis using linear regression. So, and then to come to better results. So the thing which we covered here is very in-depth, because what we have seen is we have seen how to fit linear models when the data is very pure, which is continuous values. And then we saw how the metrics can be toggled or how the metrics can be changed. The next thing which we saw here is if the data contains both continuous values and discrete values, how do we categorize them as a factor? And then how do we utilize that? So the main assumption in linear regression is that the features which we are using should be linearly independent of each other. And these stars will tell us which ones to use and which ones not to use. So if the data is linearly independent of each other, then we'll get a better model. And then, but you can use both continuous and discrete values. The only thing is for discrete values, you use the term as dot factor so that you actually clean the data first into a format which our algorithm understands. And then you fit the model. Once you look at the summary results, then you can actually find that which ones can be avoided and which ones can be used to improve the results. And if you want to avoid it, so LM Y versus what you want to fit. So this tilde means that Y versus X. So I want to predict Y versus all the features. If you use dot, it means all the features, but dot minus means I'm removing all the features but atemp, and then I'm predicting the data again. And the summary there will tell you which ones to use. So I think, is this clear? Like this is, I think, the crux of like linear regression, how to predict it in using the R case study of biking data, and also how do you deal with categorical variables, how do you deal with continuous variables and stuff. So I'll give you this, I'll send you this particular code, go through it in detail, and then try to improve the accuracy of it by removing certain fields based on the summary of your data. Once you actually see that the summary of the data actually points out to other things, then you can remove those things and then reevaluate your algorithm. Any questions on this so far?
No questions.
No questions. Okay, cool. So this is okay. So this is the linear regression in detail. So let's do another case study on logistic regression. But let's understand, why do we need to do logistic regression, right? So I talked about linear regression, in which we have one more case study on logistic. So both of them are regression, but logistic regression is a different kind of regression. We'll see why do we need logistic regression. We already learned about linear regression and polynomial regression, right? So when you want to predict like stock market data and stuff, you use polynomial regression. But when you want to do something with which has a linear shape, then we use linear regression. But there is one more regression called logistic regression. Now let's see a little bit as to why do we need logistic regression, or what is logistic regression. So logistic regression is a classification algorithm. So you did linear regression, right? So let me give you an example where you can use logistic regression. Let's say I give you that one particular team scored 320 runs. Predict and tell me whether this team can win or not win. So this becomes an example of logistic regression, because when your output here is categorical, either you win or not win. It's not continuous here. So whenever your output you want to determine is categorical, we generally use logistic regression. So whenever the regression algorithm which we want to actually estimate is categorical in nature. So given a certain model, like for example, if someone wants to ask and see that these are the team scores in IPL, can you predict which team is going to win? So in such cases, we use logistic regression. I'll actually show you one more example. If you take the voting in India, so I'll before we go into it, let me just finish this thing. Logistic regression is an example of a classification algorithm. It can be used when dependent variable is categorical in nature. So basically, when your prediction output is categorical. So in the previous case, we saw that the Y value is absolutely, like when we are predicting the count of the bicycles and stuff, it was the actual number, right? But in this case, the output value is yes or no. It has disease or not disease. Is this one of the 10 digits which the handwritten digits have predicted or not? So when the output here is a categorical value, that is when we use logistic regression. In simple words, it predicts the probability of occurrence of an event by fitting a data to a sigmoid function. We'll come to why we use sigmoid function later on. But the main thing I want you to understand is the difference between linear regression and logistic regression. Linear regression predicts continuous value. For example, you can use linear regression to predict the price of the house. But if the problem becomes, will the house sell or not for more than $1 million, that becomes a logistic regression problem. Is that clear? So why do we use logistic regression? And why can't we use linear regression in this case?
I'm just curious. Logistic name is come from logic, or logistic means transportation?
It's just the logic aspect of it, because we use probability and we use some probability metric to determine the category. That's why it's logic. It's based on that probability logic. That's why it comes from logistic. It's not transportation.
Oh, so before applying that logistic regression, and do we have to refine data up to some extent?
No. So to an extent, yes. But let's look at this example, right? So in this case, so basically, this is an example of amount, people's wealth and their voting choice for prime minister. So we saw that, like in general, right? Like you have to apply some data pre-processing such that it becomes a categorical problem, right? Because the output in case of logistic regression is basically discrete. It's not a continuous value. So in this case, given someone's wealth, can you predict whether they'll vote for Congress or they'll vote for BJP? So this becomes a logistic regression problem. So in this case, what happens is you have to first modify your data such that anyone who has an income of more than 60,000 rupees, you have to put them in Congress category, and anyone who has an outcome, a salary less than 60,000, they voted for BJP. So it is a stepwise function. So you don't see, if you plot it, it's not continuous in nature. It's either 1 or 0. In such cases, you use a logistic function to actually predict the output of this thing. So yes, pre-processing should be done, but it should be done such that there is no intermediate value. Like someone can't vote for both BJP and Congress, right? Either they vote for Congress or they vote for BJP. So when you're trying to predict one of the two, you use logistic regression. But when you're trying to predict number of votes for this Congress candidate, because that's a continuous value, right? You have some values in between also.
Yes.
That in that case, you use linear regression, because linear regression, you'll try to fit a line and try to find all the points between. Like what will happen if you do linear regression in this case? So let's say I have the data here. So I'm saying people who voted for BJP are category 0. People who voted for Congress are category 1. And this is the wealth distribution. So there's 20,000 to 140,000. So as we have seen that when they're categorical values, the line which we predict passes through the mean of both of them. In the last example, we've seen that, right? With the shoppers data, where the number of shoppers on a weekday and the number of shoppers on a weekend, if you take the data and you use linear regression on that, the line will pass through the means of both number of shoppers on a weekday and mean of number of shoppers on a weekend. So let's say if I use linear regression here, right? And then if I use linear regression, you will get a line like this. It'll try to fit as much as possible, but it'll still have a lot of errors. So let's say then if I fit this line and then I ask you, okay, someone who has an income of 75,000, who will they vote for? So if you go 75,000 and you look here, the value you're getting is 0.66. What does that mean? It's neither 0 nor 1, right? So that's why linear regression can't be used in this case. So in such cases, we use something called as logistic regression. And the line which you see is not, we won't predict a linear line, but we'll predict something called a sigmoid, which is like this. So we'll predict something which is like this, such that the change is really abrupt. So after 5, it directly becomes 1. And anything in between here, we will draw and say anything below 0.5, make it 0. Anything above 0.5, make it 1. So we are going to predict a line which looks like this instead of a straight line. Because in straight line, it doesn't predict anything here, right? It has to actually have values here and then go on up and have values here. So we cannot predict a straight line in that case when your output is categorical. Or by categorical, what I mean is when your output values are discrete. Because when I take something over here, it says that he has voted for both Congress and BJP if I use linear regression. So in such cases, we cannot use linear regression. So you see here, the red line is linear regression line. The linear regression solves exactly only of the two incomes between 15,000 and 90,000. Moreover, it predicts values less than 0 and greater than 1, which does not make any sense because the output here has to be either 0 or 1. So that's the reason we don't use linear regression. And then we go for logistic regression. So what is the alternative? Since linear regression tries to fit a line that is not giving values between 0 and 1, the function needs to be changed. It should not be a straight line. It should be something else. Instead of fitting a line, we find the probability which is between 1 and 0 of a person voting to Congress given his income. So we need to actually, instead of fitting a line, we need to find the probability given his income. You see his income here. It's whether he'll vote for Congress or whether he'll vote for BJP. So the bottom line of logistic regression is we use this function called sigmoid function for fitting this problem. In sigmoid function, what happens is you actually see, look at, this is how a sigmoid function looks. The sigmoid function is 1 by 1 plus e to the power of x. So the sigmoid function, it fits really well for our problem here, right? Because it's either 0 or 1. What if you actually come up with a value here? So if it is this thing, it is 1. If it here, it is 0, right? But there is certain portion here where the transition happens between 1 and 0. In this case also, it's still fuzzy, right? Because it's not predicting 0. It predicts 0.5, 0.8, and 0.2. So in such cases, what we do is we say that anything above 0.5, we will make it 1. Anything below 0.5, we'll make it 0. So that way, we actually will get a categorical output finally. Any questions on this? Like, why are we using sigmoid function? So first and foremost, why do we need logistic regression? Why can't linear regression solve this problem? Because if the data output is categorical, which means that it's not predicting, like in the previous example, we saw that we are predicting the exact number of byte counts which we need to store. So in that case, you're predicting a continuous variable. But if you're predicting whether someone voted for Congress or BJP, whether given these many runs, whether a team will win or not win, the output you're predicting is not a continuous. I can't say 0.8. What is 0.8? It should either be 0 or 1, right? So if I'm trying to predict whether a team is going to win the match given the number of runs, the output should either be, there's no gray area, it should either be white or black. So in such cases,
So I just wanted to clarify something.
Yeah.
So like in the cricket example,
Yeah.
if it's yes or no, then it's logistic. But what if you're trying to predict like future scores based on past scores?
That is linear.
Okay. All right.
So it's a you are actually spot on. So the thing is, when you are actually trying to predict, the runs are continuous, right? So 300, 305, 306, they are like continuous in nature. It's not like they win or lose. If you're predicting whether win or loss, then you use logistic regression because the output is either win or loss. But in case of number of runs you predict, that is actually you see that will fit this line properly, right? Because then you can say, hey, they're scoring 320 runs, they'll score 315 runs based on the previous scores. So then you use linear regression. But you're spot on. When you have to predict the output, then if the output is like black or white, if the output is yes or no, if the output is voted BJP, voted Congress, or voted Republicans, voted Democrats, when the output is categorical, where you don't have a middle ground, you use logistic regression. I think Satvik asked a question like, does it mean that logistic regression always uses sigmoid, or is there a slightly better function to use? So there have been other logistic regressions where they modified the sigmoid a little bit, but in 90% of the cases, they still use a version of sigmoid. So you can still modify the sigmoid such that the slope, this section is minimal, right? So this section spans from minus 0.4 to plus 0.4. So you can make it a little bit more stringent. So like you get something like a step function, right? Like this, and then go up like this. So, but we don't want to be that rigid in changing the distance. We want to have a middle ground somewhere. So we generally use a sigmoid, which is like this. And on top of this, we actually use one more condition, which is for sections where the output is not exactly categorical, where let's say if the value is minus 0.1, right? If you take minus 0.1, the value predicted is 0.3. It's not 0 nor 1. Then we truncate them. We see 0.3, is it greater than 0.5? No. Less than 0.5, then make it 0. So ideally, the idea behind the sigmoid is to come up with a step function which either takes the value 0 or 1, where you can clearly say whether team will lose or whether team will win, whether someone voted for Congress, whether someone voted for BJP. So is that clear?
Yeah, it's clear.
So there's also one more question here. Isn't classification also somewhat similar to logistic regression because both are giving output like disease or not? So you're right, Satvik. So in case of logistic regression, that's why the first slide here says logistic regression is a classification algorithm. The reason why we are using regression is because we are not drawing decision. Remember when I was first introducing regression to you, I said don't go by the word like it's a classification or not. Regression means when you're fitting the data to fitting a curve to your when you're fitting a curve to your data, that is regression. Whether you're solving a classification problem or a regression problem is different. In case of classification problem, you try to come up with a decision boundary. You don't try to fit an equation to your data. So Satvik, I think you're absolutely right in saying that this is a classification problem, but the way we are solving it is using regression. So regression, yes, so regression can be solved using a classification problem. Yes, that is true. But the reason why it's called regression is because we are fitting the line or we are fitting a curve to the given data. If you go with classical classification problems, we fit a decision boundary. We try to find a boundary between both the classes and say it's left of the boundary, then it is this, it's right of the boundary, it is this. But in this case, if you look at what we are doing here, we are trying to fit the given, so this is our data, right? We're trying to fit a line to the data. Whenever you're fitting a line or some curve to the data, like in this case, I'm fitting a sigmoid function to the data. So I'm not trying to segregate the bound. I'm not trying to find a decision boundary. In classification problems, we try to find a decision boundary which goes between the data points such that both sides are different classes. In regression, we try to take the data and try to fit a line to the data itself and answer questions from it. So logistic regression, the first line here is basically logistic regression is a classification problem. You are right, absolutely right in that sense. But the way we are trying to solve the classification problem is by using regression. Regression means that you are trying to fit a model to your data. But non-regression problem like SVM and stuff, they're not fitting something to the data, but they're trying to fit something between the data such that you can segregate them. In this case, it's not fitting, it's not segregating the data, but your output Y is basically trying to give you, depending on your model, it's trying to give you 0 or 1. So I hope that's clear. So the way we are trying to solve the classification problem in this is by whenever you're fitting a curve to your data, that is regression. What you do with it, whether you're predicting or you're classifying, it's in mandatory. So regression, that's why it's called logistic regression. In logistic regression, the main point to take away is your output is categorical, yes or no, win or loss, vote for one party or the other. So you don't have anything in between. So that's why we actually try to model something which looks like a sigmoid function. The reason for that being sigmoid is, the reason why we use sigmoid is because sigmoid is going to be 0 for anything beyond 5 till minus infinity. And it's going to be 1 for anything above 5. I mean, in this case 5, but depending, it's just one example of sigmoid. But this is my, so, whenever X is like really big from there, so it is always going to be 1. It's always going to be 0 whenever X is less than this. In the middle portion, we need a threshold. If the threshold is above something, we will truncate it to 1. If it's below something, we'll truncate it to 0. So logistic regression can be used to answer classification problems, yes or no, has disease, does not have disease, win or loss, and things like that. So I think, I think let's go forward. So we will then see how this logistic regression is actually modeled also. In linear regression, we saw that the model is to find the values of W such that it fits this a straight line, right? So we actually, that's what we did in the 10 minutes back. We tried to find what is W such that Y equals X, W transpose times X. This will result in a straight line. But in logistic regression, Y will either take the value 0 or 1. So you cannot have this model. So in order to do that, we actually take the output and put it in a sigmoid. So this H here is a sigmoid function. So the only reason we actually did this transformation, so it's still predicting the values ax plus bx plus b, but we put it in a sigmoid function. So the output now becomes y equals sigmoid function is 1 by 1 plus e to the power of minus w of x instead of having w transpose x. So in logistic regression, this is how we remodel the equation. So then so that's why we use sigmoid. The reason we use sigmoid is because for values x greater than something, it will always be 1. For values x less than something, it will always be 0. So that's the reason this thing is transformed into a sigmoid function. Let me see in this. So again, there is a lot of math behind how we solve this. We can still use gradient descent method to find out what these values are. In linear regression, we used LMS algorithm in which we minimized the cost or the error function, which is defined as this. In logistic regression, the cost function we will use is slightly different. It's going to be the cost function is going to be the same thing, but instead of y transpose this thing, we will use the sigmoid function. So when we do that, because sigmoid is to the base e, right? So when e goes to the other side, it becomes log. So we kind of get a different cost function. We still use the same thing to optimize it. By using the above cost function, the classifier will return the probability whether a sample belongs to class 0 or 1. By assigning a threshold to the probability, we can always say whether it belongs to 0 or 1. For example, if the probability greater than 0.3, then it always belongs to 0 or else it belongs to 1. So the thing, what it's trying to say is we try in areas where the probability, or this is a probability function, right? Because probability also lies between 0 and 1. But for probabilities which are in between, we try to put a threshold and then put them and make the output categorical. So that's how we actually come up with the threshold and then put it in a categorical problem. So the performance of logistic regression, you always use. So everyone understands what true positive is, false positive is, true negative is. I think this is really important to understand because we always use we always use confusion matrix to predict. So confusion matrix, so let's say if you're predicting something good and bad, right? Let's take two categories. If the actual values are good and actual values are bad, and we predict good and bad. So if we predict good with good, we say it is true positive. If we predict good as bad, we say it is false negative. So the way to remember this is the second term here, positive or negative, belongs to the prediction. So we're predicting it as positive means we're predicting it as good. Predicting as a negative means we're predicting it as bad. False tells you whether it is correct or wrong. So let's say now in this case, true negative. That means what? You've predicted it as negative. True negative means you have actually taken a bad sample and predicted it as bad. So that's why it's called true negative. True positive means you predicted it as positive. It's true. That means that it's actually positive. False negative means you've predicted it as negative, but the output is wrong. That means that you predicted a good sample as a bad sample. False positive is the other way around. So I think they use this a lot in data science. They say this is false positive. So the thing how you decode that is the second term. Second term means that what you have predicted. So positive means you predicted it as good, but it is false. That means you have predicted something bad as good. So these are the terms which you basically need to understand really well, because the way these logistic regression problems are actually the way they are evaluated is based on this false positives. And so there's something called as ROC curve, which we will see later on. I don't think we'll get into the details of it, but when you actually the ROC curve is actually plotted between true positives and false positives. So basically on this section. The reason we try to do that is because I think we have the next slide on that. So ROC curve. ROC stands for receiver operating characteristics. So let me actually expand this a little. Let me go to full screen. I think this is the ROC curve. So ROC curve is always plotted between true positive and false positive. But why do we actually plot this? The reason for that is because you always want a curve which is having high true positive and less false positive, right? So if you have, so anything which is above this line, so anything like this, if you always can find a curve which has like high true positive and less false positive, that is your best result. But you'll always have a parameter to choose that from. Like in this case, this is your parameter. What is your parameter? This threshold. You see this threshold here, which we set here. In this case, I said like 0.5 was the threshold, right? So you will always get a different ROC curve for 0.5 threshold. You'll get a different ROC curve for 0.2 threshold. You'll get a different ROC curve for 0.8 threshold. So how do you know which threshold to choose? Then that's how you will draw an ROC curve to evaluate. So the yellow line may be for threshold of 0.2. The pink line may be for a threshold of 0.4. The purple line maybe is for a threshold of 0.8. So you basically plot your true positives and false positives on this graph, and then you will evaluate to see which one is closer to, the yellow one is the best, because we always want something which is which has a high true positive and less false positive. So we always choose an ROC curve, which is basically dependent on what threshold we want to use. Is that clear? So let's see what ROC stands for, right? Receiver operating curve is one of the very common ways of assessing the usefulness of a binary classifier. Is an ROC curve, which means the way they evaluate it is called area under the graph. So area, because if you see the yellow line has more area under it, right, as opposed to the purple line. So whenever you plot an ROC curve, if it has a higher area under it, that's just a mathematical way of seeing it. But the reason why it has higher area is because it has this really steepness towards true positive rate and less steep towards false positive rates. So that's the reason we have true positives and false positives. So it's a simple plot that shows the trade-off between true positive and true negative for various choices of probability threshold. So if you have different probability thresholds, you'll have different graphs, and you will see that the best way to pick that is basically by using a graph which has higher area under it. The other metric which you see is called AIC. It's something similar to R2 square. Let us actually do a simple, there's nothing much here, and rest is the code. So I actually wrote the code and put it in the slides. So at this particular point of time, let us actually, this one we will write together. So let's actually create, it's a very small code. It's 1, 2, 3, 4, 5, 6. 6 lines of code. So let's do a regression problem for this particular data set. So there's one data set which I sent called adult.csv. What that shows is, it shows of all the adults in a particular county, it shows their income. Let me open that. So this is the data set for, I think it is for New Jersey, or I don't know which area. So it shows the age of the person, his or her qualification, whether they're married or not, what is their relationship status, what race they belong to, how much do they earn, and which country do they belong to. So this is this data set, which is the country of origin and stuff. So using this data set, we want to predict to see how much is their annual income. So it's just because now we are not predicting exact annual income. If you want to predict exact annual income, it becomes linear regression. we are going to categorize it. We're going to predict whether he has an annual income greater than 50,000 or less than 50,000. So we want to learn, this study is done because we want to see how the income distribution is within the adults of certain county, whether race plays an effect in it or not, whether the education plays a role in the income or not, whether the kind of work they do play a role or not. So these are the other things which we want to answer with this data set. So quickly, I think I sent you this thing. It's called adult.csv. So it is the data of all the adults in certain county and their annual income. So what we will do here is we will use 70% of the data to fit our logistic regression model, and then use the rest of the data to predict how the results are. So let us write this this thing. Then we will go through it and analyze how we can actually use our summary. Again, this is also the summary will tell us a lot of things. So it's very simple. So put the adult.csv in the same file as where you're writing logistic regression. Read the CSV file, and then first make it into a category. How do we make the into category? Anything which is below 50K, we will put it as 0. Anything which is above 50K, we'll put it as 1. So we will convert the last column into zeros and ones. And then we'll fit a logistic regression model for the income versus only two columns. As homework, you can use other columns. I'm just using the race of the person because I want to see if there is inequality in the race. Like, is it a black person? Is he earning more? Is a white person earning more? And then I want to see if there is some gender inequality. I want to see if like male people are earning more or female people are earning more, right? So I'm just using two columns in it. So as I told you last time, this tilde operation is y versus this, right? So if you want to use all the columns, you just do a dot. But if you want to use only some columns, you can just say tilde, race, and this thing, and then use a binomial. So GLM is basically the logistic regression fit, but I'm using the category for using sigmoid function is called family equals binomial, and this is my data set. Let's fit a logistic regression model to this and see the summary. And the next one is where we predict the thing and plot the confusion matrix. But it's just 1, 2, 3, 4, 5, 6, 7. 7 lines of code. Let's quickly write this.
Sai, I could not install RStudio because it was just throwing some error. So I'll just listen to this class and do it once the class is over.
Okay. But were you there for linear regression?
Yeah, I just, I mean, for some time I was not there.
Oh, okay.
Sorry, today it was.
No worries. Because I was actually asking like who else is coding, so I didn't hear from you. So I assumed.
No, I could not code today. I'll just do it using the recording. I'll just do it. And
okay, perfect. So this is the logistic regression part of the code. So if you like bring up your RStudio models. So it's really interesting. So the summary actually tells you a lot of things, right? So it's the same thing here, but instead of the only difference between logistic regression and linear regression is in logistic regression, there is something called as the AIC. You'll still have those stars and stuff. We'll tell you which ones to use, but instead of R squared, which was there in linear regression, there is something called as AIC criteria. Higher the AIC criteria, so lower the AIC criteria, the better is your model. So how do we get to that? So I've actually taken this adult data set and I want to see how the income is distributed based on gender and based on race. So I'm predicting, so let me run this. I took the adult data set. Firstly, I converted the columns into 0 or 1 and I made them as like above 50K is 1 and below 50K is 0. And then I fit this model for logistic regression. The reason we are using logistic regression here is because of the fact that our prediction is basically a categorical output. Because we are either predicting 0 or 1. There cannot be anything in between. And then let's look at the summary here. The summary is very interesting, right? Because it has the same things here. See, it tells you that in the race, there is basically male, there is white, there is other. So it is telling that, hey, black and other races don't matter that much because it's not giving it 3 stars. So you see so the stars here show the significance of each of the factors, right? So if it again like 3-star, that means 99.99% it is confident that this thing can rely on the data. But if the races are something else, then if you avoid the data, your model will be much predicting it much better. So and similarly, like in the sex, if it is male, then it's giving a 3-star. So it is showing you which portions of it are linearly independent and which ones can you remove them from this thing. So the whole point in the prediction is to choose which features to actually use, right? If the features which we use are linearly dependent on each other, then we might have then the model will not learn well. So and okay, and also look at the degrees of freedom. So remember I was talking about degrees of freedom here. So there is something called as degrees of freedom. Degrees of freedom means that you have that much excess of data. AIC is also another thing. So the lower the AIC, the better is your model. So you can change your model. Instead of taking race and gender, you can take something else to predict your model and then see if your AIC is coming down. There are a couple of things here which I wanted to talk about. It's something called null deviance. What does null deviance mean? Null deviance means that if you don't take any data, if you only take the intercept value. So by the way, this is firstly the main reason we got this thing is these are the estimates of the coefficients for each of the values. So when we took the race, we have like 4 races, right? 1, 2, 3, 4 races. These are the coefficients for each individual race, and this is the coefficients for male. So this is the prediction which it got. This is the estimate is the main thing which we are doing in regression, right? The model which we are trying to predict is because we want to predict what are the coefficients of each variable we are using. Firstly, these are the coefficients, and then it is telling you which ones to use for better results. 3-star means it's very confident. The other ones means it's not confident. But mind you, if you remove the other one, that's not the only sole criteria. Don't only go with the star rating here. The main thing you need to optimize is AIC. Sometimes it'll tell you this is good for predicting, but if your AIC score doesn't come down, then don't remove that particular feature. So having said that, I think I didn't talk about null deviance. Null deviance means that, so when you're predicting, you're actually predicting A1, A2, A3, and up to B, right? The null deviance means when you use only B and make all others 0. That is called null deviance. The main interpretation of null deviance means that, let's say if you don't have the data and only use the intercept, because B doesn't have B is a singleton, right? It's not associated with any feature. It's A1x1 plus B2 A2x2 plus A3x3 plus B. So the B doesn't have any feature associated with it. So null deviance is the output you get when you only use B and make everything else 0. And then residual deviance will tell you. So if residual deviance is less than null deviance, that means that, hey, when you have your data, when you have A1, A2, A3, you have better result. The lesser the deviance, the better. So take some time to analyze what this summary is. So first thing, what the summary tells you is, firstly, it tells you the coefficients. It tells you which coefficients are relevant. It tells you what the residuals are, like how much is the error coming from these residuals. And then it gives you this thing, which is AIC. AIC, the lower the AIC, the better is your result. The lower is your deviance, the better it is. Null deviance and residual deviance, the difference between both of them is, residual deviance is the deviance you get when you use all the parameters, A1, A2, A3, A4, A5 up to B. Null deviance means that when you make A1, A2, A3 all 0 and only use B, is it better? That means that, is the data even helping you? Definitely it is helping you, because if you use only the constant B, you're getting 35,000 as your deviance. But if you're using A1, A2, A3, it means that 34,000 is definitely less than the thing. So this tells you that, yes, definitely use this data to use this race and sex to actually predict the income. But you have to improve further, because this is not the optimal one. So the assignment to you is, use different features, assign the, assess the summary, see which ones of them are higher, which ones of them have, which ones of them give you lower AIC. So now let me just do another model. I'm going to like copy this thing. You can code it along with me if you guys are like. So now I'll create another model in which I don't want to use the race at all. I just want to use to see the gender if it is having any relevance. So one good thing about R is I can just select lines and run it in the middle. Okay, now let's take a look at both of them, right? Did it change? Was adding race helping us or not? So look at the AIC score for, it was 34,000, and look at the AIC score now. 34,200, but earlier was 34,000. So that means the AIC score was, so again, remember, lower the AIC score, the better is your model. That means if I include race, then it is better than just including the gender. But let's say now not race, right? I'll actually use some other features. Let me look at maybe education, right? Let me see if education plays any role. So from this thing, I first found out that adding race is giving me lower AIC score. So I'll add race to it back again. Adult. So dollar is for column names, right? So if you do column name, it'll directly show you which, like all the column names. So I'll use race, and now I'll use education. I'll see if there is any correlation between how much you earn and how much you're earning. So how much you earn and how well educated you are. Let me use education. And now let me run my model again to see. Wow. So the reason why you see education, it is actually dividing them because it's a categorical variable, right? Education, bachelor's. So it divides it into each categorical variable given education. So adding that, look at the AIC score, it improved much better. So earlier it was 35,000, 35,000, 34,000. Now adding education, it brought it down to 29,000. Oops. Something happened. I don't know why it has shown this. Anyway, so let's. So adding education, you can see that it brought down the AIC score further. So this will tell you, like, using logistic regression, which is the better, like which are the features which will help you predict better. And look at this thing. It's saying all the most of the education, the things which it is helping it to predict better are in education also. Summary. In education, it didn't matter from 9th to 11th class if you finished your education, stopped your education at 9th class, 5th class, 6th class, 1st to 4th, 11th to this thing, it did not matter because all these things gave you the same result. That means you didn't have a degree. But when you have degree, like associate commerce, when you had bachelor's, when you had doctorate science, some professional school, that mattered more because all these things were irrelevant, right? All of them are interdependent on each other. In fact, all of them are dependent on, see, preschool, and all of them are the same thing. So look at it's really smart to tell you, like, hey, there are no stars here. That means that all this data are dependent on each other. So if possible, remove this data from your database and give it to me again. So is this clear? Like, how do you actually analyze this? What is null deviance? Do you see that null deviance is always going to be the same? Because null deviance means that you're making all other coefficients for each features to be 0 and only using the standard bias coefficient, which is just B. A1, X1, A2, X2, all A1, A2 up to AN are 0, and only you're using B. And if you use that, what is your deviance? And if you use other parameters, how is it improving? The lower deviance, the better it is. So yeah, you can actually play around to see which ones actually give you better AIC scores and stuff like that. And you can fit logistic regression models to this. and predict it. So the last step is, this is how, so mind you, this is until this stage we're still training it. All these are predictions, but so all these are just analysis of how our training data is behaving, right? And then the next step is basically we predict using these features, we then predict our output. And then how do we actually determine the thing? So we actually need a threshold also, right? Because in logistic regression, for the areas which are not exactly 0 and 1, we actually have a threshold. I use a 0.5 threshold, and let's see the confusion matrix. So this is the confusion matrix. You can see it's doing a pretty good job. It predicted. In confusion matrix, we actually have the diagonal elements, right? You see the sum of the diagonal elements is much better than the other two. So therefore, we did a pretty good job by including education into our equation. So that kind of completes my lecture on logistic regression and regression in general. So any questions on this? If you guys are coding, I'll give you some more time to code, but I'll actually, I want to use the next 10-15 minutes to show how you can write an R web service using Azure ML or anything of that sort. I don't know if all of you have accounts, but before that, any questions on this thing? Satya, were you able to code this, or are you still working on it?
I'm still working on it.
Okay, I'll give you like 2-3 minutes more.
Okay, sure.
Until that time, I'll see if anyone has any questions.
Okay, sure.
Any questions on like why logistic regression or how to? Meher, Satvik, Jatin, Deepika, anyone? Any questions?
No questions, Sai. I'll
Are
just.
there any combination where we use logistic and linear both together, or it's not feasible?
No, there are for example, let's take the example which Satya was talking about, right? So there, let's say if we are having like a cricket team, and there someone asked this question about two questions, right? Like they gave the performance of some cricket team and said, okay, this is how much they scored, this is how they won or they lost. So if someone asks you the question of can you predict how much will they score in the next match and whether they'll win or lose? So in that case, you basically use logistic and linear regression together. Assuming that their pattern follows a linear, their scoring pattern is linear. If not, you will use a polynomial regression. If their scoring pattern is up, down, up, down, up, down, up, down, 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 like if it doesn't follow a linear pattern, then you use polynomial regression. But then if you want to predict whether they are going to win or lose, you'll use logistic regression. So in that case, like if someone asks you the question of predict how many runs they'll score in the next match and predict if they'll win or lose. So that case, you'll use both. You'll take the features and use both logistic and linear regression together. The main idea behind logistic regression is if your output value is a categorical value, that's when you will use both of them.
Okay, that's fine.
I finished coding.
So basically, were you able to use the summary to actually? So this is actually a very powerful tool because it tells you a lot. I mean, I've done this in Python also, but Python, you have to actually have a lot of, the summary is a very cool thing which will tell you an insight as to which variables to use, which variables not to use, how is it depending, because until this step I'm not even doing prediction, right? It's going to analyze the training data only and tell me. In general, what we do is we do prediction and then see, oh, if the output is good, then we go change variables. But using the summary of the model, that's a very nice thing because at this point, I'm not even doing prediction. I'm still using my training data to tell and asking it to tell me like which ones to use, what to, and how to analyze this and stuff. So like I found this like summary thing really useful because it'll tell me a lot about like what can explain more about the data and stuff like that. So in this case, I can turn this easily into a linear regression problem also. How do I do that? Instead of saying to predict whether they'll earn less than 50K or more than 50K, if I ask you how much will they earn, that becomes a linear regression problem because I'm changing the output prediction from categorical to continuous value. So if I change the output data income, so let's say I give you like, okay, someone has done masters, someone did bachelor's, this is their ethnicity, this is their gender, this is their, if I give you an observation of like all these parameters which I had here, all these parameters like which working class, where do they work, whether they work for this much time, how many hours per week do they earn, work and stuff like that. So given all this data, I can easily, and then I can change this problem into a prediction problem. But the reason I did not do it is because I don't have the exact income values. If I had the exact income values, I can make it into a linear regression problem. So I only had the values whether they were earning less than or greater than 50K. So that's why it becomes a good case for logistic regression. So that kind of concludes my session on logistic regression. I'll just take a minute to where is my I wanted to, yeah. So I wanted to show you a quick thing on, I don't know how many of you actually use Azure ML or use Azure in general, but Azure has this really cool thing called as Azure Machine Learning Studio. So what they do is they, on the cloud, they'll give you you can actually create a VM for your own uh, own experimentations and stuff. So if you act, I mean, I think all of you have some free credits. So this is something I'll just introduce to you. If you want to play further, you can. I think Azure offers, at least for students, I know that they offer a lot of free credits and stuff. So play around with this thing. So there in this section, this thing is called Azure studio.azureml.net. If you go create an account and log in, you can create different experiments in here. So I actually created a bunch of experiments. So you can actually go and say, hey, I want to create a new experiment. So I did one experiment on frequent pattern mining. So frequent pattern mining is the algorithm which is used in case of Amazon and other places where if you actually, if someone bought a Xbox, they'll recommend them buy HDMI cable. So, and also nowadays, like even Walmart and stuff, right? They use this frequent pattern mining algorithm to put product placements. Let's say you're going to buy home groceries, right? So let's say you bought. If you actually look at the stores these days, they're very smart about where they place their product. If you buy eggs, they'll place milk right next to it, or they'll place bread right next to it. So that someone, when he's buying eggs, if he sees milk, he'll go and buy that. So they actually do this frequent pattern mining where they look at patterns and then they try to predict which ones you'll buy next. So there's an algorithm in R called ECLAT. So it's a very simple algorithm. So I actually wrote that in. So if you actually look at this, it's a very simple algorithm. I wrote it in R. It's basically called ECLAT, and then you pass it some transactions that will predict. I'm not going into like R code here. I just wanted to give you like a thing where you can go and say, I want to create a new experiment, and then you can create a web service from it. So when you create a web service, it's like drag and drop thing. So you can, when you say I want to create a web service, it'll give you a web service input. You can put your R code in R module. So there's an R language module in on Azure ML. So you can go put, you can even put Python language module also. So
Anna, I have a question. Or
Yeah.
maybe not a question, like a request. I was wondering, can we maybe do this with like the liver patients and see from start to end how we create an experiment, how we can run it?
You can. So, but then I did not write that. So basically, this one is something I had already written.
Oh, okay.
But you, do you guys have free credits in Azure?
I'm not sure, but we might, like you said.
So if it is there, so basically, you actually when you actually launch your, let me go back to this thing and let me go back to my experiments page. So the way you actually do this is, we can do something. So when you come to your Azure ML Studio, so this is something on the cloud space where you can put your algorithms. They'll give you a, they will give you your own machine to run this thing. So you can go create new. So it'll ask you like what kind of experiment do you want to run. So I just want a blank experiment, right? So you have other things also. You can there's an easy way to download the UCI database. There are some data sets given in Azure ML only, but let me create a blank experiment. So in the blank experiment, it'll tell you like which ones to drag and drop and stuff. So I want to first create let's say I want to create an R module, right? I'll create an R module. I'll say execute R script. So this is my module. I'll just put it here. And then I want to make it into a web service. So I'll just create this thing. And I want to take the input of the web service because my input of the web service is where I'll get my data from. Oops, sorry. And then I have my output of the web service where it is my, so these are REST endpoints. So, I mean, I don't want to get into like web services and all, but when you just look up REST endpoints and it'll tell you. So basically from the web service input, you get your data in the JSON format. I was talking about it last time, and then you'll connect it to your R script. Is it not connecting? Connect. So now your R script, you write your R script here. So it'll give you like this default thing here. Like you can actually port other things also. Like let's say if I'm using some particular zip files, I'll just create an R module here. So create R module. And here I'll actually tell which runtime I want to use, which zip files do I need to have, and I'll just put them in. Oh, so let me actually. So no, this is not R. I'm sorry, this is not R module. You actually create a zip file here. It'll help you unpack the zip file, and then like if you have your custom code written, right? If you want to use standard things, you can just write it here. So you have your R script here. So it actually mapped the port for you. So you have the data set already in data. So whatever you want to do with data, like I did the thing for pattern mining. So I wrote my code here, and then I gave the output to this web service here. So I gave my output of the result of the data and I put it in this web service. And then I actually deploy my web service and then I run it. So if I do that, then it will publish a web service. So I'll show you something which I had already created. Okay. So this is the one for pattern mining. So one second. Go back to this thing. So it's giving me the config. Oh, sorry. This is the web service, right? Sorry. This is my. So it still stores my thing. So once I create my web service, I already published this. I say deploy web service. So in this case, I have like, so this is my zip file, which I actually had my own custom files and I put it as an input here. And then I had my R script. I have my web service as an input to this thing. And this one will actually execute my R script and give it to as an output. And once I deploy my web service, I can go to this. So this thing is the web services section. I can go here and then I'll see, okay, this is my web service, right? So I created one here. I can find out its endpoint. So this is the API key. I can just use this API key and then send my data to this. So I can create a web service where I can take my data and then use this API key and send my data as a JSON format to this. So once I publish this, now this is on the cloud. So you can always, So it's like a web REST service endpoint which you have written using your machine learning algorithm, and you can write code. Anyone can use it. So if I give permissions or if I give this API key, anyone can use. So you can create your own startup by publishing all these things onto your web server, and then advertise to people that, hey, if you want to do like classification using support vector machines and stuff like that, use this endpoint. So you can just give it for free, and then all the computation, everything is done on the cloud, and then you'll give them back the results. So they need not understand the logic behind what you're doing or how you actually make this. I mean, if you have Azure ML credits, I would encourage you guys to play around. Like, everyone can publish one different algorithm which you feel you're confident about, and you can create like uh, multiple web services, one with support vector machines, one with neural networks, one with logistic regression, one with k-means clustering. So each one of them can become a REST endpoint, and you can expose them uh, to public for free. And then if anyone wants to actually run some experiments, all they'll do is they'll give their data as a JSON endpoint to this, and to this endpoint here using this API key. You'll get the data, you'll process it, and you'll return them back. So that is something really cool you guys can experiment and do. So I just thought, I mean, this is I thought in case if you wanted to like publish something on the cloud, this is something very useful.
So this Microsoft Azure machine learning is free?
I don't know that it's free for me. I'm not sure. I know I think they have something like $100 or $150 credit for everyone. So it's definitely free if you want to run one or two experiments. But if you are doing more, I think they'll charge you. But for students, I know it's free. So they have like free subscription and stuff. But for if you're signing up for as a new developer portal, you'll get like $150 worth free. So you can still, it'll be enough for you to like publish. So in this case, so like what is SaaS, right? Service as a platform, infrastructure as a platform. So this is service as a platform. So they won't give you the whole machine, but they'll just give you enough resources to run your own code. So it won't charge you more than 150. So I'm pretty sure every one of you can write one module definitely and put it up there, and then you can then access using the API key and then send the data to it. It'll be a fun exercise to do if you're interested in doing. Any questions? So I think that kind of concludes today's class. So today is the last lecture. So if you have any questions, definitely send it to me on my Gmail. I don't check the Premiere one that often, but my Gmail is my personal account, so I keep checking that. And yeah, I'm looking forward to seeing how, like, if you guys end up like, I'll be more than happy if you guys end up in like pursuing data science as a career, and the future, if we can collaborate sometime, that'll be really cool.
Thank you very much, Sai. It really helped me because I did not have any clue about this field. Now I have a brief overview of what this field is and what kind of problems can be solved with this and all that.
Yeah, this is actually I mean, it says introduction, but we went a little bit more deep. We covered like most of the algorithms and stuff.
True, true.
But advanced, if you want to take advanced courses, right? So deep learning is really advanced. So we did a little bit, we touched on like what CNNs, RNNs are, but deep learning is a more evolved and this subject. So that is really good. And if you have any feedback, you can definitely send me or Vardhini Garu. Like, I think she is the one who's. So I'm not part of Pramea. Vardhini Garu's initiative, it's Pramea. I just teach there. So I like teaching, and I hope like you guys like can take home something from it like I know it's been Wednesdays and Sundays and stuff, but I hope like you guys understood at least like it's a start for like data science and understand how the problems are, and I hope the coding and exercises have been useful. I tried my level best to like try, but then it's like again as I said, right? It is uh, I mean it's not in person, and it's this thing. So any feedback you guys have, you feel free to send to me or Nigal, and yeah, and and definitely send me your resumes. I'll definitely try and help to see if I can at least I'll what I can do is I can forward to the people in the other areas of who I know, and if any opportunity comes,